Blackbody radiation, Planck's law. Color and spectral class. The light emitted by stars consists of a mixture of all colors, but our eyes, and brain, perceive such light as being white or tinged with pastel color. In fact, different stars have varying amounts of each color in their light. This causes stars to have different colors. Most people, however, have never noticed that stars come in a variety of colors. When light from the sun, or any other star, is passed through a prism, it is separated into its component colors, a continuous spectrum. When a beam of white light is passed through a prism, it is broken up into a rainbow-like spectrum. Color and spectral class. If the spectra of different stars are analyzed, it is found that the intensity of the various colors differs from star to star. Relatively cool stars have their peak intensity in the red or orange part of the spectrum. The hottest stars emit blue light most strongly. In other words, the color, or wavelength, of the maximum intensity depends upon the temperature of the star. The star is not necessarily the color of the maximum intensity. In fact, there are no green stars. Max Carl Ernst Ludwig Planck 1858–1947. In the late 1890s, Wien and Rayleigh had unsuccessfully attempted to formulate an equation expressing the intensity of electromagnetic radiation as a function of wavelength and the temperature of the source. In 1900, Planck derived the equation empirically. By December of 1900, Planck had derived the equation from fundamental principles. Max Planck, 1858–1947. Planck's law: intensity of radiation versus wavelength. The intensity, I, of electromagnetic radiation at a given wavelength, is a complicated function of the wavelength and the temperature, T. Planck's law: intensity of radiation versus wavelength. Planck's law: radiation intensity versus Planck's law: radiation intensity versus wavelength at 3000 OK, note peak in infrared. Planck's law: radiation intensity versus Planck's law: radiation intensity versus wavelength at 6000 OK, note peak in visible. Planck's law: radiation intensity versus Planck's law: radiation intensity versus wavelength at 1000 OK, note peak in ultraviolet. Planck's law: actual radiation intensity versus Planck's law: actual radiation intensity versus wavelength at 3000, 6000, and 1000 OK. Planck's law: intensity of radiation versus Planck's law: intensity of radiation versus wavelength. Normalized intensity versus wavelength. Planck's law: normalized intensity versus Planck's law: normalized intensity versus wavelength at 3000, 6000, and 10,000 OK. Planck's law: normalized radiation intensity versus Planck's law: normalized radiation intensity versus wavelength at various temperatures. Planck's law: normalized radiation intensity versus Planck's law: normalized radiation intensity versus wavelength at various temperatures, where ET equals total energy radiated per unit area over all wavelengths. Stefan Boltzmann law. ET equals T4, where ET equals total energy radiated per unit area over all wavelengths, and equals 5.670510 to 12J. CM2SK4. E.T. Wilhelm Karl Werner Otto Fritz Franz Wien 1864–1928. In 1896, Wilhelm Wien unsuccessfully attempted to derive what is now known as Planck's law. However, he did notice a relationship between the temperature of a glowing object and the wavelength of its maximum intensity of emission. The result of his investigation is now known as Wien's displacement law. Wilhelm Wien, 1864–1928, Wien's displacement law. The peak of the emission spectrum of a glowing object is a function of its temperature. The hotter the object, the shorter the peak wavelength. Wien's displacement law gives Lmax as Ft, which allows us to calculate the temperature of a star if we know the wavelength of its maximum emission, which is easy to measure from its spectrum. From Planck's law, take d/dl, set equals 0. Then, Lmax equals 2.8979106 nmK. Example, Lmax for the Sun equals 502 nanometers. Therefore, T equals 5770 K equals 5500 C, the three types of spectra: continuous, emission line, and absorption line. Sodium absorption lines. The sodium vapor subtracts out the yellow lines from the continuous spectrum emitted by the source. As an excited hydrogen atom returns to its ground state, it emits the extra energy in the form of a photon with a certain wavelength. Each energy transition within an atom gives rise to a photon of a particular wavelength. Solar spectrum, original drawings by Fraunhofer. Absorption lines in a star's spectrum reveal the presence of elements and compounds. Absorption spectrum of the Sun. Continuous spectrum. Absorption spectrum of the Sun. Bright line spectrum of sodium. Bright line spectrum of hydrogen. Bright line spectrum of calcium. Bright line spectrum of mercury. Bright line spectrum of neon. The inverse square law: when light from a point source travels twice as far, it covers 4 times the area, and is therefore only 1/4 as bright. THEEND